Okay, here we are, moving on. We should have finished up working on the GeoGebra activity where you're finding the incenter using the angle bisectors. So this first slide here just basically takes us through a couple of vocabulary words just to make sure we remember some things here. So concurrent, all that the word concurrent means basically is, in terms of geometry, means you have several things meeting at a single point. Several lines meeting at a single point. There are a lot of things that can be concurrent. You can have, basically concurrent means at the same time. So like sometimes basketball games are running concurrently, which means they're running at the same time. So it just means at the same time or same point. A point of concurrency is where in geometry three or more lines meet. The circumcenter, as we've already learned, is the point of concurrency for perpendicular bisectors. And now what we're going to talk about today is the incenter, which is the point of concurrency for angle bisectors. Just recalling here really fast, a perpendicular bisector, if you have a segment, the perpendicular bisector, you find the midpoint of that segment, and the perpendicular bisector goes through it at a right angle. And then when we did that in a triangle, we found that those perpendicular bisectors met at a circumcenter, and we found out that the circumcenter can lie inside, outside, or on the triangle. Angle bisectors, remember, are in a triangle, like so. If you pick an angle like that, angle bisector goes out from that angle and splits that angle in half. It does not necessarily meet here at a right angle or anything like that. It does not necessarily meet in the middle of that line. Basically, all an angle bisector does is it breaks that angle in half. And when you have all three angle bisectors, they meet at the incenter. So let's look at a little bit more information about the incenter. Okay, the incenter theorem, the incenter is the point of concurrency for angle bisectors. Okay, we already kind of talked about that on that previous slide. And you made angle bisectors in GeoGebra. Okay, the incenter is equidistant, meaning the same distance to the sides of the triangle, and it is always inside the triangle. So when we say equidistant to the sides of the triangle, these blue lines here in the diagram are the distance from the incenter to the sides of the triangle. The reason they're marked as perpendicular is because anytime we find a distance from a point to a line, we always use the perpendicular distance. So for instance, if I was to ask you, what is the distance from this point to this line or this segment here? You wouldn't tell me that the distance, you'd calculate it by coming over here. That's not the distance. Okay, the distance would be from the point to the line would be going straight down and being perpendicular to it. So if we look at our picture, okay, we have ND is 5x minus 1. Okay, so if we zoomed in here, ND is 5x minus 1. And NE is 2x plus 11. NE, that's this one over here, is 2x plus 11. Okay, so there's our given information if we want to think about it that way. And we want to find NF, which is this other blue segment here that we don't know anything about. So the first thing we want to think about, we've talked about circumcenters and we've talked about incenters, but if we look at a picture and there's all of these red lines and blue lines and everything that you see, how do you know if something is an incenter or a circumcenter? Well, remember, a incenter is where the angle bisectors meet, and if you look, these markings in the corner tell me that those angles are being bisected. So that tells me if these angles in the corner are being bisected, that I'm talking about the incenter of that triangle. So that means it's the incenter, and what we just learned on the previous slide is that the incenter is the same distance to the sides. So we know those blue lines, these three blue lines here, are all going to be the same or equal, which means we can say that 5x minus 1 equals 2x plus 11. And if we solve that, we subtract 2x, we get 3x minus 1 equals 11. If we add 1 to both sides, we get 3x equals 12 and x equals 4. So we just have to be careful here. It's not asking what is the value of x, it's asking what is the value of NF. Well, we said all three blue lines are the same, so whatever ND is going to be the same as NE, is going to be the same as NF. So if we put x in for either one of those, we can say 5 times 4 minus 1. Oops. Times 4 minus 1. 20 minus 1 is 19. So this length right here is 19. And it should also be the same length as NE over here. So if we did 2 times 4 plus 11, 11 plus 8 is 19, which means this one here is also 19. And since it's the incenter, this one is also 19. Okay, let's look at this one. We've got some perpendicular marks, we've got blue lines, we've got red lines. In the figure, QM is 3x plus 10. So QM, that's from here to here, is 3x plus 10. And QN is 7x plus 2. So this guy here is 7x plus 2. And if we look, we all want to talk about, is it the incenter or is it the circumcenter? Well, these angles here are being bisected. If those angles are being bisected, that means that it is the incenter, and all three of those blue lines in here are going to be the same, so they're going to be equal. So you'd have 3x plus 10 equals 7x plus 2. And if we go ahead and solve it, if we subtract 3x from both sides, I get 10 equals 4x plus 2. If I subtract 2 from both sides, I get 8 equals 4x, and x equals 2. Now it asks me what is QP. Well, basically, I can put 2 back in for any one of these expressions up here. So if I said 7 times 2 plus 2 is 14 plus 2, which is 16. If I put it in over here, I would have 3 times 2 plus 10. 3 times 2 is 6. 6 plus 10 is 16, which means that all three sides, this one here is 16, this one here is 16, and this one here is also 16. So PQ is going to be 16 as well. Okay, the last thing I just want to think about here a little bit is if I have this weird looking intersection over here where nothing is quite meeting at a nice right angle like a lot of times they do at intersections if you drive around a lot. So you have this kind of triangular shaped intersection, and the city wants to put a lamp post on the boulevard, shown that the lamp post is the same distance from all three streets, okay? Which means they want it to be the same distance from that street and that street and that street, okay? If we want something to be the same distance from the sides, those are basically the sides of the triangle, we would want to use the incenter because those are sides of the triangle, and so we would want to be the same distance from the sides, it says, so we'd use the incenter. But what if we wanted the lamp post to be the same distance from the intersections of the streets? Well, the intersections are here, here, and here, which are the corners of the triangle, or the vertices of the triangle. And if we want to be the same distance to the vertices of the triangle, then we would want to use the circumcenter. So this would be an example of, depending on what your goal is with finding a center, if you want to be close to the streets, you want to be close to the corners, you want to be different places, you might use different centers of a triangle. So that was just kind of a more of a real life example kind of thing. We will continue working through centers of triangles, and please let me know if you have any questions.